In our first session of gear metrology, we have discussed different terms related to gears, involute gears. In that, we have discussed about line of action, pressure angle, and involute function. We also discussed about how the involute profile of gear tooth is generated by keeping base circle as a reference. Now, there are so many features in gear, but the very basic feature and very important feature is gear tooth thickness. First of all, we know what is gear tooth thickness. If you just consider this diagram, then in this diagram you can see one gear teeth here. This one gear teeth. Then on pitch circle, these two involute profiles, two opposite involute profiles of same gear teeth cuts this pitch circle at these 2 points. Then arc length of pitch circle between two opposite involute profiles of same gear teeth. That is what called as a gear tooth thickness. Gear tooth thickness is very much important property because that defines the proper rotation or the motion transmission between two gears. That's why we are not discussing all the different methods for different features measurement. We are only discussing about how to check gear tooth thickness error. Okay, so we'll be discussing three methods. One is gear tooth vernier caliper, second is base tangent method, and third is the constant code. So first we are starting with gear tooth vernier caliper. So here you can see we have considered one gear teeth of entire gear teeth. So this is one gear teeth. On that one gear teeth, this curve is called as a pitch circle. If you look, it's a part of pitch circle. This curve is representing part of pitch circle. So radius of this arc is r, which is pitch circle radius. Now, if you look, then what is called as a gear tooth thickness? Gear tooth thickness is length of arc on pitch circle. Length of arc on pitch circle cut by two opposite involutes of same gear teeth. Means if you look here, this A and B are the intersecting points between pitch circle and this involute profile. Then you can see here one arc A, E, B and one chord, one line A, D, B. Then gear tooth thickness is A, E, B. It is not A, B, B. And we know it is very difficult to measure arc length. So far we have only discussed about instruments for linear measurement and angular measurement. We are not having any instrument which can measure length of arc, and gear tooth thickness is actually length of arc on pitch circle cut by involute profiles of same gear teeth. But if you look here, ADB and AEB, they are having very minor difference. Then they are having very minor difference in length. And if you look, if you move from top to down, then gear tooth thickness is continuously varying. As we are moving from top length to root of gear teeth, then gear tooth thickness is continuously increasing. So actual gear tooth thickness is on pitch circle. So that's why if you are using gear tooth vernier caliper, then gear tooth vernier caliper is having that capability. This image is indicating you how gear tooth vernier caliper is used to measure actually caudal length, ADB. Because as we know, we are not able to measure AEB. We are not able to measure arc length. So that's why we are measuring ADB, caudal thickness. This ADB is called as a caudal thickness. This AEB is called as the actual gear tooth thickness. But as you can see in this diagram, difference between actual gear tooth thickness and caudal gear tooth thickness is very less. So that's why, as we are not able to measure AEB, then let's measure ADB. But we need to measure ADB exactly at distance D from point C, from top line. Yeah. So you should require instrument which can measure this both the dimensions. Means that instrument should have capability to measure line length ADB at depth D. So that's why if you look in this diagram, in gear tooth vernier caliper, we are having two verniers which are right angle to each other. Same is represented schematically in this diagram. So this is one gear tooth. So what we are doing, this D depth we need to set on vernier B. We need to set depth D on vernier B, and that you keep on top length of gear tooth, and then after if you close this vernier E, then that will, these two jaws of vernier E exactly make contact with the involutes at point A and B. So gear tooth vernier caliper is having that capability because it is having two scales. One scale that will be used to set depth D. At that depth, if you close this horizontal jaws of second vernier E, then they exactly make contact at point A and B. They make exactly at contact on pitch circle, and then you measure ADB. Okay, so this is basic procedure to measure gear tooth thickness. But as we know, why we need to measure gear tooth thickness? Because we know it is not possible to manufacture any component with the required dimension, required exact dimension. Always we need to allow some variation, some tolerance is always there. So we, after manufacturing, we need to cross verify whether manufactured component dimension is within the close tolerance of required dimension or not. So that is what we are doing. But as I told you, in this process, we are not measuring AEB, we are measuring ADB. So we are not actually measuring gear tooth thickness, but we are measuring caudal thickness. So this W is called as a caudal thickness, and the depth of caudal thickness from top line is D, which is called as a caudal depth. So D is called as a caudal depth and W is called as a caudal width. So first of all, we need to derive relation of W. If AEB gear tooth thickness, then what should be the ADB length? What should be the caudal width? Actual caudal, required caudal width. So that will be our required dimension, and same we will be measuring by gear tooth vernier caliper. So gear tooth vernier caliper, that will give us actual dimension. So we cross verify reading of gear tooth vernier caliper with the theoretical W. So here we are using this diagram again. So we need to derive equation for W and equation of D, because how much depth we need to measure W, that is important. So first we try to derive this D. So here caudal depth D, if you look in this diagram, this D is equals to O to C. If I take distance O to C, then what is O to C? If you recall, O to C is called as a addendum circle radius. O to C is called as a addendum circle radius. From O to C, if I minus O to D, If I minus O2D, then what I get? I get small d caudal depth. Clear? So D is equals to O2C minus O2D. Now how much O2D? Because if you look here this ADB line, if I connect point A and B with the center of gear wheel, then I get one triangle here, OAB. If I split this triangle, then I get one right angle triangle, two right angle triangles actually. One is ADO and second is BDO. Okay. So now next I need to find out what is OD. Then looking to this right angle triangle, if I apply sine rule, then sine theta is equals to AD by OA. AD by OA. Now how much OA is? OA is pitch circle radius. So I can say OD is equals to R sine theta. Now theta is equals to 90 by N, where 90 degree divided by N. N stands for number of teeth present on particular gear. Now how this theta is equals to 90 by N, that we will try to understand. So just consider one gear wheel. Then if you look, what I need to find out? I need to find out, suppose, angle covered by one circular pitch. This is called as a circular pitch. This is called as a circular pitch. This much of distance is called as a circular pitch. Then how much angle of this arc? Because this pitch circle, that is having total angle, because it's a circle, so total angle is 360 degree. Now from 360 degree, if I divide 360 degree by N, number of teeth, then I get angle covered by one circular pitch, means angle by this arc. Okay, if I half that angle, then what I get? I get angle covered by one gear teeth on circular pitch, means this much of angle. If you look this cursor, then this much of angle. But we want actually theta in this diagram. We are going back. If you just look, theta in this diagram, theta is half the angle, covered by one gear teeth. Then if you look here, angle covered by circular pitch, one circular pitch, that is 360 by N, as we have seen in previous slide. Angle covered by each tooth thickness is half of that. So 360 divided by 2N, then we get 180 by N. Then this angle covered by AEB, means this total angle, means angle 2 theta angle is equals to 180 by N. But I want theta, so again I need to divide this 180 by N by 2. Then I get theta is equals to 90 by N. So that's why this is how theta comes to 90 by N, where N is number of teeth present on gear. Now, so I got relation of OD. Now relation of OC. See, O to C distance. Then O to C I can write as O to E plus E to C. Now what is O to E? E is present on pitch circle. So O to E, I can say radius of pitch circle plus E to C. What is E to C? If you recall terminology, then E to C is addendum. Then E to C is addendum. Now if you recall empirical relations which we discussed in previous session, then this addendum is equals to 1 module for any involute gear. So here I am writing O to C is equals to R plus N. Okay, so we got both OD and OC relations. So let us write D is equals to OC. So OC is 2m. I am just putting values of OC and OD in equation of small d, caudal depth. So R plus m minus R sin 90 by n. Now, if you simplify this, then you get finally this equation. What we have done here, we have written this R in terms of module and number of teeth. This pitch circle radius is written in terms of module and number of teeth. For if you just consider hint, then module is equals to d by diameter of pitch circle divided by number of teeth. Now diameter of pitch circle is 2 times the pitch circle radius. Then module m is equals to 2 times r divided by n. Then I can replace simply r is equals to nm by 2. So just write here r is equals to nm by 2. Right here also r is equals to nm by 2. Then take nm by 2 common. Then finally you get this equation of caudal depth. Okay. So this is the equation for caudal depth if gear to thickness is correct. Similarly now, next we need to also find out equation to find what should be the caudal width if the gear to thickness is correct. Then if you look here, this W is equals to 2 times this W in this diagram is A to B. Now A to B is equals to 2 times A to D, this much. Now again we use this right angle triangle, and now we apply sine rule. See, one correction here, instead of sine we need to consider here cos. You just make one correction. In the caudal depth equation, instead of sine we need to take cos, because we need to apply cos rule. Because here to find OD we need to apply cos rule. So cos theta is equals to O to D divided by O to A. So please make that correction. So in this entire derivation you have to use cos, and finally in equation you get cos. But in case of W, you have to apply sine rule. So sine theta is equals to AD by R. Then AD is equals to R sine theta. So we got R sine theta. So that is half of the caudal thickness. We want full caudal thickness, then multiply by 2. Then we get caudal thickness is equals to 2R sine theta. Now R I can write as nm by 2. So write here nm by 2, then 2 will be cancelled out. Then your final equation for caudal thickness is nm sine 90 by n. So we got both the relations. So these are the theoretical relation for caudal width and caudal depth. Now what we need to do? Now we need to use geared tooth vernier caliper. Here you can easily count number of teeth on any gear wheel. So count number of teeth on any gear wheel. Put in this equation. You know module of gear wheel, because during the time of design of particular gear wheel we have selected some module. So M is known to you. So you can use you can solve this both the equation. So you get theoretical value of caudal thickness W, and you also get theoretical value of caudal depth D by these two equations. Now you got theoretical value of both. Now what you need to do, just go to previous diagram here. Now what you need to do, you need to set D, theoretical D on vernier B. So this is the movable jaw of vernier B. So you set some depth D here, and then as you place that movable jaw on the top end of gear teeth, and now if you close vernier E, then that vernier E will measure the caudal gear tooth thickness. So this instrument now will give you practical value of caudal thickness. So now you have two values of caudal thickness. One is practical by gear tooth vernier caliper, and second is analytical by using this equation. So if you take difference between practical value and analytical value, then that will give you difference in the caudal thickness. And if difference in the caudal thickness, then that is indirect indication that there is also difference in the actual gear tooth thickness. So in this way, using gear tooth vernier caliper, we can find out error present in gear tooth thickness. So it is indirect method actually, because we are not directly measuring gear tooth thickness, but based on caudal gear tooth thickness, we are judging whether actual gear tooth thickness is correct or not. Okay. So we are ending here today's session. In next session, we will discuss about base tangent method. Till that, just refer this video and try to understand gear tooth vernier caliper method.